Let me start by first thanking the organizers for having invited me to talk about one of my favorite topics. Uh, I'm only sorry that it can't be done live and that I won't have a chance to have personal interactions with those of you that are watching this. But in any case, it's great to be here. What I want to do is to talk about the quantum internet. I want to provide some background and then drawing on some of the work that I've been doing, talk a little bit about what I see as some of the research challenges in this area. So first of all, why the quantum internet? Well, it turns out that there are a growing number of distributed quantum applications spearheaded by quantum key distribution, where the need is that you have parties, let's say, uh, in different parts of the continent or different parts of the country that want to be able to generate physically secure keys. And they need a network in order to be able to do that. The second is that there's a growing number of small quantum computers, and there's a need to be able to connect them. These computers are not particularly large, so they can't handle very large problems, but the hope is that if they're connected with a network, that it may be possible to develop distributed versions of various algorithms, like Shor's algorithm for factoring large numbers, that can then be executed in this setting. And there are other applications having to do with sensing, let's say, of phenomena within the universe, high precision clock synchronization. So let me tell you what we're going to cover in this lecture. I'm going to start off by giving you a Quantum 101 tutorial, and then I want to present some of the networking challenges that quantum provides, and follow that with some discussion of work that I've done having to do with understanding the capacity of a quantum network, what the benefit of path diversity is in doing end-to-end entanglement. And after that, I'll summarize and draw some conclusions. Okay, so let's start with Quantum 101. And let's first review a classical bit. It has only two values, 0 and 1. And it's represented by a physical two-state device. An example is a light bulb, where the states are either it's on or off. It could also be a circuit, where the states correspond to different levels of the voltage. So in the quantum world, we have the analog quantum bit. It's sort of abbreviated as a qubit, and it represents a two-state quantum mechanical system. Okay, and just as an example, you could have a photon, which can be polarized in sort of all different directions and with different phases. Here I've drawn two particular polarizations in the horizontal and in the vertical plane. And these are defined to be qubits in states 0 and 1. The quantum world has come up with this bracket notation developed by Paul Dirac. And so state 0 would be referred to as, let's say, ket 0. And you can think of it, it's just a column vector. And likewise, ket 1 is represented by another column vector. And by the way, something that we're going to see is that we can think of these as orthogonal to each other, and they form a basis, as we will see in the next slide. So it turns out, of course, that an electron can be polarized at lots of different angles. It also, there can be a different phase with it. And so the general state it can be made up as a linear combination of the states 0 and 1, where the coefficients, alpha and beta, are complex in nature, and they satisfy that when you square them and you add them, they sum up to 1. So we have, if you think about it, an uncountable number of states that this qubit can take. And so it's interesting to ask, well, what can we do? Can we characterize it in any way? And the answer is that it's difficult. But I want to talk about one particular operation that you can apply to it that allows you to learn something about it. And it's a measurement operation. And taking this polarized photon as an example, a measuring device would be a beam splitter. And so you would pass it through this beam splitter. If it were in state 0, it would essentially be reflected up. If it were in state 1, it would go straight through. Now, suppose that this photon is in a superposition state. Then it turns out that one of two things will happen. It will either go straight out and be a 1, or it'll go up and be a 0. But both of them cannot happen at the same time. So this measurement you can think of as destructive. We have a superposition state that comes in, but in the end, we either get a 0 or a 1. Now, if we repeat this many times, the fraction of times that we will get a 0 is equal to alpha squared. And the fraction of times that we get a 1 will be equal to beta squared. And so that's one way that we can use measurements to sort of characterize what's going on. But there's more to it than that. So we've talked about a single qubit. You can have a 2-qubit state, in which case you have 4 basis states corresponding to the combinations of the 2 qubits being in the 0 or 1 state. You can have a superposition state, which will be a linear combination of those 4 basis states with coefficients that are complex, that when you square them and add them, they sum to 1. I want to mention a key concept of entanglement. We say that 2 qubits are entangled when the state of one of them cannot be described independent of the state of the other. Okay, and I'll illustrate it with a simple example called the Bell state, and where what we have is the 2 qubits are in a superposition of 0, 0 and 1, 1. And so notice that if we know that the first qubit is 0, then necessarily the second qubit is 0, even though it's possible in this superposition for it to be 0, 1. So we can't describe the second qubit independent of the first qubit. So this Bell state is interesting. Suppose that we give the first qubit to Alice and the second one to Bob. Okay, and Alice decides to measure her first qubit, and as we see, she will either get a 0 or a 1, and with probability 1/2. It's easy to calculate. Now, if she measures a 0, then when Bob goes to measure his state qubit, he's going to get a 0 as well. If Alice measures a 1, then necessarily when Bob measures his qubit, he will get a 1. And that's sort of the illustration of this entanglement that I was talking about. And this is useful because you can generate shared randomness across distances. You can generate lots of these Bell states, give the first qubit to Alice, the second to Bob, and whenever they go to measure, they will always generate the same random sequence of 0s and 1s. And this is the basis of quantum communications, computing, key distribution. So, talked about how this is useful for when Alice and Bob are separated. And it brings up the question of how do we allow that, or how do we get make that happen? So suppose we have Alice with 2 qubits in state psi naught and psi 1. She could transfer the first qubit to Bob. Unfortunately, quantum information is very delicate, very sensitive, and so there's a very good chance that it will get lost or dropped or changed. She might generate this state again, and the same thing could happen. But maybe eventually she'll succeed to get it to Bob. The probability of success, it turns out, is given by this expression e to the minus alpha L, where L is the distance between Alice and Bob. This is for an optical fiber. And the important thing to note is that the probability of success decays exponentially in distance. It turns out that for classical bits, this decay is much slower. It's essentially a power law. So what can we do in this case? Well, the community has introduced the idea of a quantum repeater, which you would place, let's say, halfway between Alice and Bob. It would have memories to store qubits. And then the way things would work is that each of the links would generate a Bell state, let's say, across. And because this repeater is half the distance, the probability of success essentially increases quite a bit. And the second thing would be that the repeater would do a Bell state measurement, or what's called a Bell state measurement, on the 2 qubits that it holds. And that has the consequence of propagating the entanglement to the end nodes. Okay. Putting just one might not suffice to increase the probability of success. So you could have a string of repeaters, and each of the links between them would generate these Bell states. You would do simultaneous Bell state measurements at each of the repeaters, and if everything succeeds, you'd end up with an end-to-end Bell state. Okay, so let's say that Alice and Bob have this Bell state, and now Alice wants to send a qubit to Bob. It turns out that there's an operation called quantum teleportation that can essentially take advantage of, let's say, this end-to-end entanglement to do so, and I'm going to illustrate it. So Alice has a qubit that she wants to transmit to Bob. We have a repeater in the middle. The links generate link level entanglement between the repeater and Alice and Bob. The repeater then does a measurement, and if it succeeds, that you will now have a end-to-end entanglement, or a Bell state, between Alice and Bob. And so now what Alice does is she essentially constructs a Bell state, an entanglement with between her qubit and the one she wants to transmit. She does a measurement. The measurement is going to result in 2 classical bits. We don't know what the result will be until the measurement comes up, but let's say it's 1, 0. It's going to destroy the entanglement with Bob, but Bob will still have his qubit. And what Alice does is to send those 2 bits to Bob, and then Bob applies a correction and ends up with his qubit in the same state as the qubit that Alice wanted to send. Okay, so now we've talked about sort of a line of repeaters. What we're really interested in is a network. And so think of it that we're going to have a collection of quantum switches that will be connected via lossy links. These switches will have quantum memories as part of it. And basically, what how the network will operate is that the links will essentially go through two phases repeatedly. In the first phase, the links will try to generate bell states between the switches. And then in the second phase, the successful bell states will be used with a measurement to try to connect, let's say, the bell states and propagate them to an end-to-end entanglement, as we see, let's say, here. Okay, and so this concatenation of bell state measurements and these bell states essentially realize, you can think of them as end-to-end entanglement flows. And you can think of it, every time one succeeds, we're generating an E-bit. So with that in mind, I'm going to just give you a flavor of the kinds of challenges that we have. First, there's a question of what kind of service the network should provide. I've been talking about it as if what it's doing is generating end-to-end entanglement, so distributing entanglement to end users. But another way that you could construct it would be along the lines of a classical network where its purpose is really to transfer quantum information. Now, these two are essentially equivalent because I showed you that if you generate entanglement, then it's possible for Alice to transfer a qubit. Another challenge is, what should the data plane look like? What should the control plane look like? What we might expect, at least initially, is that the data plane will be quantum, but the control plane will be classical until we understand how we could do it in the quantum domain. There's a question of should both of these planes be on the same physical network, or should we have separate networks? Another challenge, and which I'm going to be talking about, has to do with resource allocation. You have lots of users that want to use the network for generating entanglement, and so the question is, how do you share? We saw that if you want to generate end-to-end entanglement, you need sort of a sequence of links and switches, and so there's a question of path selection, or think of it as routing. Of interest to me as well is, how do you model the performance of this network? And how do you measure it? How do you monitor it? How do you do management? Okay, I'm going to be talking a bit about the resource allocation and the performance modeling, as that sort of goes with the work that I've done over the last few years. But first, let me say a little bit about a quantum switch. Okay, we've got interfaces here with 4 interfaces. We have quantum memories where the qubits are loaded into and they can be read out of. We need the capability of being able to do quantum measurements, these bell state measurements that I talked about. We need to be able to let's say, perform quantum logic across the qubits held in quantum memories. We would like to be able to generate entanglement within the switch itself, and that would require sources for photons. And then, of course, we need to do classical computing and communications. So with that in mind, I want to talk about the capacity of a quantum network, okay, when you have, let's say, multiple users. So one of the important aspects of this is that the information that switches have about, let's say, the rest of the network has a big impact into the decisions and the scheduling that it does. And so we might want to have global state information. That may not be possible. There may be the network has no state information, or perhaps it has some information, but up to L hops away. So clearly the amount of state information is going to affect the achievable, let's say, capacity region. And of course, the upper bound is determined by what we can achieve with global state information. So let's look at a simple example. We have this dumbbell topology. We have two Alice-Bob pairs. And think of it that these these are segments that are connecting the different nodes, not a single link, but let's say multiple links. And suppose that we have no state information available, but we can coordinate between the switches, okay? So what we might do in that case is some kind of time sharing, time division multiplexing. And so what I'm showing here is essentially the capacity region. The x-axis corresponds to the rate that the first pair is getting, the y-axis to what the second pair is getting, and what we would achieve using time sharing would correspond to this blue line right here. If we had global state information, then what we would do is the switches would analyze, let's say, this information, see which links were able to successfully entangle, and then choose which pair to create an end-to-end entanglement if possible. And that would correspond to, let's say, a region given by this red line right here. Suppose that we don't have global, but we do know the results of link entanglement one hop away, okay? In that case, what we might expect to achieve would be something better than time division multiplexing. I'm showing it here as this green line, but not, of course, as good as if we had global state information. I should mention that the way that you would get a point on this green line is you would do time division multiplexing. And so in the case where you could generate a end-to-end entanglement for either pair, then some fraction of time you would do it for one, some fraction for the other. But if you could only generate for one, you would always do it for that one. Now, it's interesting to ask, what if we have no state information, and also that, let's say, these two switches can't coordinate? Well, the best that we could do there is some sort of a randomized policy. Okay, if we look at the two switches, we'd have some probability such that the Bell state measurement would be done between these two qubits, and 1 minus that between these two if both were possibilities. And likewise here. And if we look at the capacity region for that, what we find is we get a huge penalty from not having any coordination. We get this really ugly concave region. So that's just sort of giving you a flavor of what some of the issues are in the context of a network, in this case, a simple network. We have also looked at, of course, a single switch connected to, let's say, a population of users. And so suppose that this switch is serving K users, and it has storage, infinite amount of storage. And let's suppose that each link can successfully generate entanglement at a rate μL for link L. That Bell state measurements succeed with probability Q. We've developed a model for this that has allowed us to calculate the capacity. The capacity is really very straightforward. It's the aggregate link entanglement rate divided by 2, because you need 2 link entanglements in order to generate an end-to-end entanglement, and then essentially thinned by Q, the probability of a successful belt state measurement. We've extended this to more complicated states, n-partite state, and I'm illustrating one where we have, let's say, 3 qubits. We have 3 end users. We have 3 successfully generated belt states on the links connecting them to the switch. And there's what's called a Greenberger-Horn-Zellinger measurement, or a GHZ measurement, that can be performed to entangle the 3. And this n-partite GHZ state is written as follows. And if you look at it, you see it's just a generalization of the belt state, but where you have n qubits instead of 2 qubits. And this is useful in lots of applications. And after sort of a very complicated analysis, we've been able to derive, in the case of a homogeneous system, this really intuitive capacity expression. Aggregate link rate, we are dividing it by the number of parties in the entanglement, and then we have to thin it by the success probability. And we have an expression for the mean memory usage. Okay, now I'd like to turn our attention to a different issue having to do with path diversity and entanglement rounding. So we're going to look at this in the context of a grid network where we have, let's say, Alice and Bob, and there's some probability P associated with each link of being able to generate a successful entanglement. And if you recall the operation, the first phase, we generate link entanglements, and I'm showing the ones that succeeded. And then in the second, we perform bell state measurements, let's say with success probability Q. And if we do it right, in this case, we will end up with 2 end-to-end entangled paths between Alice and Bob. So the question is, how do we do this? What is the rate that we can get? And let's suppose that we have global state information. In that case, it turns out it's an NP hard problem to come up with the optimal policy. But suppose that we just use a simple heuristic, a greedy shortest path algorithm. We set up the links, and then we decide the measurements such that we have the shortest path. And after that, we then take the next shortest path and so on. And if we do that, then we get the performance shown on the right. What we're looking at is a 3D plot, the logarithm of the rate as a function of the distance along the x-axis and the distance along the y-axis. And here I'm showing 2 essentially surfaces. One where the link success probability is 0.55, and you always have successful measurements, and the other where it's 0.45. And it's interesting, when it's 0.55, we get essentially a distance-independent rate. When it's 0.45, we get a rate that decays exponentially. And you might ask why that is, and it has to do with percolation properties of a 2D grid. Namely, a 2D grid percolates at a link probability that's larger than 0.5. Okay, so now it's interesting to ask if we can come up with an upper bound, and we have done that. If you have always succeed in your measurements, it just corresponds to the maximum flow. That's easy to obtain. If measurements are not reliable, then we have a trivial upper bound that's 4 times the greedy rate that I showed you before. And here again, we have this 3D plot showing the behavior of the upper bound compared to what we get using this greedy global information policy for several different pairs of link success and Bell state measurement success probabilities. So this all has to do with global state information. So what can we do if we only have local state information? And we've looked at a very simple policy, which I want to describe to you. We're going to focus on this switch U. We're going to keep track at each of the switches, the Euclidean distance from that switch to Alice and from that switch to Bob. Okay. And I've written them for the neighbors of U. Okay. And that's what we're going to use to determine what qubits to measure. So let's see what happens. Suppose that at the end of the first phase, we generate one successful Bell state. Well, in that case, we can't do anything. If we generate 2, we don't have any options. You should just go ahead and measure these 2 qubits. But suppose that we generate 3, and now you has to decide which pair to connect. So what it does is it looks to see if everything were to succeed, which of those would give rise to the shortest Euclidean distance. Okay, and so in this case, it turns out that the shortest Euclidean distance would go like this. And so you should just go ahead and measure these 2 qubits. Suppose that all 4 links successfully generate Bell states, then U does the same thing. It first of all connects the 2 that have the shortest Euclidean distance, which turns out in this case to be this pair. And then it doesn't waste these, it just goes ahead and connects those as well. Okay, so that's the basis of this very simple local state information algorithm. And so if we look at the rate that you get using this local rule, again, what I'm doing is I'm showing it here on this 3D plot. It's this middle surface right here. Above it, we're comparing it to the rate that you get using this global greedy algorithm. And I've also added another surface, and that is, suppose that the only thing we do is we just try to connect whatever is the shortest path between Alice and Bob. Don't take advantage of any diversity whatsoever. And so that's this R-lin surface right here. And what's important to note is that the decay rate is higher when you just use the shortest path than it is if you take advantage of the diversity. Okay. Now, I want to talk about multiple flows, but before I do that, I want to point something out that's interesting. Here we're using Bell measurements, and it turns out, may not have been obvious when, as I was going through, that the end-to-end entanglement rate that you get between Alice and Bob, it will always decay exponentially with distance when the success probabilities are less than 1. What we have discovered, though, is that if you do more complicated measurements, let's say what you try to do is 3-qubit measurements and generate these 3 partite GHZ states, then there is a region, there are values of P and Q such that the end-to-end entanglement rate does not depend on the distance between the users. And here's an example obtained through simulation. We're looking at the rate, the entanglement rate, as a function of the link success probability. I forget exactly what the Bell state measurement success probability is. And we're looking, these different colored dots correspond to distance between Alice and Bob. And we see that they all have sort of the same sort of behavior. There seems to be a critical threshold, after which then you successfully generate a state between Alice and Bob with probability almost 1. And the important thing is that independent of the distance between Alice and Bob. Okay, I'd like to, before we wrap up, say a little bit about what happens when we have multiple flows. Let's take this grid and let's put 2 Alice-Bob pairs where they're one above the, that Alice is above Bob, okay? And the question is, what should the switches do now? Well, one possibility is they just, we just share the switches using time division multiplexing. And in that case, here I'm showing the rate region. This is for pair 2, this is for pair 1. And if we do time sharing, then we get this blue line, and we can achieve anything below it. It turns out that we don't have to do strict time sharing, that there are situations where switches realize that they can't help, let's say, the pair that owns the resources at that time, and instead can decide to help the other pair. That will extend the capacity region out a little bit. But last, of course, is if you essentially give or dedicate resources, let's say, to each of the pairs, then you, in this case, you can get a huge increase in the capacity region given by this yellow line. Let's look at a different situation where the pairs essentially have to cross each other. And so there's going to be some sort of congestion area right here. Again, we could just do time sharing. And if we look at the rate region, it's given by this blue line right here. It turns out, as I said in the previous slide, there are times when switches realize that they can't help the pair that own the resources, and they should go ahead and try to help the other. And that extends the capacity region out a bit. And finally, of course, we could dedicate resources, let's say using this sort of bell hourglass shape regions, where Alice and Bob would own these switches and these switches, and then here they would own, let's say, 2 of the interfaces coming out of this switch. And of course, we can sort of control this by the angle here. And that will give you some additional benefit. Okay, so that brings me to the end of my talk. Just to summarize, one of the things that I hope you get across from this is that these quantum networks are going to be focused on distributing entanglement, and that this is very different from the classical data transfer service. And so, because of that, it introduces a variety of new problems and old problems that come from the classical domain appear, but with new wrinkles. And so, there's really a need for performance models, need for uh, resource allocation algorithms, and since this is a entanglement distribution service, there are going to be interesting questions about, how do you distribute and how do you manage entangled state? And so last, I just want to leave with you the notion that research on quantum networks is in its infancy, and there are just many, many exciting problems. So thank you for listening to me.